actually we started with the linear momentum and we discussed about that center of mass of a system. Center of mass of a system. And we also find out the center of mass for point mass distribution and also for continuous mass distribution, right? So those are the topics actually discussed in the previous class. Alright, so let's start today's topics. We say that linear momentum of a system, so it can be said F net should be del P divided by del T, right? So that's mean if you want to change the momentum of a system, you have to apply the force on the system, and that force must be a external force. So what do we mean by that external force? Let's say you have a arbitrary shape of object which has the different point mass, because that object should be sum of this lot of point mass inside of that, right? Let's say I choose only two masses. One is ith particle and another is that jth particle. The force on this ith particle, it should be force on I provided by J, and this is the force on jth particle provided by the I. That should be by the Newton third law, because this is the force on ith particle provided by jth particle, and by the Newton third law this ith particle will also apply some force on the jth particle. So this means these two forces are equal magnitude but in the opposite direction. So that's when they will be cancel out each other, right? So that's mean as a result the contribution of one particle for the other all of the particle, whatever the forces they will be applied on that, they will be cancel out. So this means the net force on this ith and j and the kth particle will be 0 ultimately, which is actually the net force provided by the internal particle. But I know, so for this ith particle or the jth particle, I choose the ith particle for arbitrary. So there will be one more force on this jth particle by some other external force. So external means, by writing this external, I'm going to say that outside of this object there will be a lot of other stuff or other things. Those things is also going to apply some force on this jth particle, right? And that's the force on the jth particle provided by the some external system. So that's we are saying that external force. If the momentum of a system is going to be conserved, this external force has to be 0. Then the momentum of the system is going to be the 0. So that's mean if this external force on that system is going to be the 0, I'll write down the del P would be equal to the 0, which means that del P actually the change of the momentum, right? We'll write final momentum minus the initial momentum is equal to the 0. Then we can write it should be Pi should be equal to that Pf, right? From here we can say that the momentum of this system is going to conserve only if the external force of the system is 0. Internal force has no business for the conservation of the linear momentum. So momentum will be only conserved if the external force on the system is going to be the 0. Alright, let's say I have a ball which I throw towards the wall, and before it strike the wall, it has that velocity v, and that velocity is going to be strike the wall with some making an angle, the theta, and the ball will leave the surface with the same velocity v, making an angle is also the theta. So that's mean before the impact velocity and after the impact velocity are exactly the same, and also the angle are equal when is going to be strike or when is going to be leaving the surface. Now the question is that whether the momentum of this system is going to be conserved or not. What should be the momentum over here? Will it be 0 or it will be different? If it is 0, then the momentum will be conserved. It is not equal to the 0, then the momentum is not going to conserve, right? Can anyone tell me whether the momentum of this system is going to be conserved or not?
Sir, it's going to conserve.
Is going to be conserved. Yes. Is there any other opinion? Alright, let's check that. So since it's basically that two-dimensional motion, I'm going to take this component of this velocities. Let's say I choose the color. This is that velocity of that part is the Vx, and this is actually that Vy. I'm saying that this is actually the Vx, and this is actually that also that Vx, and that should be that Vy. Alright. Now I want to check that what should be the change of the momentum along to the x direction, and what should be also the change of the momentum along to the y direction of this system. It's not equal to 0, I have to check that one. Alright, so change of the momentum along to the x direction, I'll write, so final momentum, that means p of x minus pix, right? P of x actually the final momentum along to the x direction, and pix actually the initial momentum along to the x direction, right? So that's actually the makes the difference. So I can write this would be pfx would be mvx minus mvx would be also that, because why it is so, because its initial velocity and the final velocity are equal and angle are equal, then this component must be the equal, right? So that's why I write down mvx and mvx over here, which means it should be 0 over here. So change of the momentum along to the x direction is going to be the 0, which means I can say that momentum will be conserved over here along to the x direction. Alright, now what about along to the y direction? I'm supposed to say along to the y direction is it should be mvfy final momentum along to the y direction minus it should be mviy, right? Now this mvy I can write down the simply, let's say y component final velocity, this vy minus this mviy would be also, there is a minus sign over here, minus mvy, because look at this magnitude are equal, y component, because this angle are same, magnitude is same, then this component and this component will be also the same over here, but the direction is different. Initial component is along to the negative y direction, and final component is along to the positive y direction over here, right? Then I can write del py would be simply mvy plus mvy, which means that this del py is going to be that plus 2 mvy, right? Which means that it is not equal to the 0 over here, right? Interesting thing actually, for the same object along to the x direction the momentum is conserved, but along to the y direction this momentum is not going to conserve. Now the question is why it is so. the momentum along to the x direction is conserved because there is no force along to the horizontal direction once it releases from your hand. The force is only towards that vertical direction, which is the gravitational force, right? Once you release the ball, after releasing from your hand, only the force acting on the ball, which is the gravitational force, net force, and it is towards the downward direction. Then it means that there is no force along to the horizontal direction, so that's why external force along to the horizontal direction is 0, so that's why the momentum is conserved along to the x direction, whereas along to the y direction, since the gravitational force is acting in the vertical direction, so that's why it acts like an external force on that ball, so that's why the momentum is not going to conserve along to the y direction. As a result, the total momentum of this system is not going to be the conserved because there is some external force acting on this system. So that's why the answer should be the momentum, total momentum of this system is also not going to conserve because there is external force, is the gravitational force acting on that system. All right, do you understand?
Yes,
Yes,
sir.
sir.
All right, let's say consider one-dimensional uh, collision or head-on collision. Sometimes we say that head-on collision. So let's write down. So I'm writing in terms of conservation of the linear momentum actually. Then I'll also define what is the collision over here. So let's say collision is simply that interaction between the particle. So it's a physical interaction actually. After the interaction, there will be some change of the properties of the system. So that's how we define actually that collision. There are two types of collision. One is the elastic collision, another is the inelastic collision. There is one more collision which is called the completely inelastic collision. I'll come to later. Right now, this. Let's talk about this. Excuse me. Let's say this is my M1, which is moving at a V1I. Let's do M2 V2I. This is the before the collision, and after the collision, which is M1 V1F, and this is M2 V2F, right? So this is actually that after the collision. Then the momentum will be conserved actually if you can write total initial momentum actually that total final momentum, then M1 V1I plus M2 V2I equal to should be M1 V1F plus M2 V2F. Right? This is actually
Yes, sir.
we
Yes,
can
sir.
write the conservation of the linear momentum of this system. So whether it's a elastic or inelastic collision, in every time the momentum of the system will be conserved. Why? Because we'll actually that conserve it is the velocity just before the impact and just right after the impact. So we'll assume that momentum of both case actually is going to be the conserved actually. So let's define that collision. Collision we define it is actually that interaction between the two particles. There are two types of collision. One is we define that elastic collision. Elastic collision. Number two is inelastic collision. So elastic collision has to be the two condition. One is actually that is initial momentum would be equal to that final momentum is kinetic energy initial equal to that kinetic energy final. Inelastic collision should be, so initial momentum must be equal to that final momentum, and kinetic energy initial is not going to be that kinetic energy final. That's the difference between the elastic and inelastic collision, which means that in the elastic collision both the momentum and the kinetic energy will be conserved. So that means there will be no loss of the energy from the system, whereas in inelastic collision the momentum will be conserved but the kinetic energy is not going to be conserved over here. And most of the case in our real life we face this is actually that inelastic collision because in that case actually when a collision actually the occur or accident occur at the road, we will find out we can hear some sound energy, right? That's the energy is going to be lost from the system. You cannot reverse that energy into the system. It could be lost as a heat energy, it could be lost as a sound energy as well. So that's why in that case that kinetic energy is not going to conserve. Those are actually the inelastic collision, and most of the collision in your real life we face is inelastic collision. And elastic collision is possible if you can create only in the laboratory system. In that case, if there will be no loss of that energy of the system, you will find out that would be the elastic collision. There is one more collision we define, which is completely in elastic collision. Completely inelastic collision, that is actually the happen when the two systems interact. After the interaction they stick together actually, so that's when they move with a common velocity. Let's say this is m1 m2, this is v2I, this is the v for the impact. So after the impact they will stick together at a common velocity is v, which is m1 plus m2, which means they stick together. Then the type of collision is known as actually the completely inelastic collision. You can say the example, if you drop an egg, that egg is going to be that shatter into the floor. So right after the collision they stick together, that is actually the completely inelastic collision. And you can say if you drop a ball, if the ball is going to be the, or a marble actually, if you drop, or a steel ball is going to be strike into the mud and it will be inside the mud, right? And then it will be also stick together. That's called actually the completely inelastic collision. And in the case of completely inelastic collision, remember maximum amount of energy will be the loss from the system. And that's why when accident is occur, if the two car actually stick together, then the maximum amount of wreckage can be occur actually in the case of accident in the road. In that case actually it's become the acceleration would be very high. Due to that high acceleration, so people can be die actually. That happen actually in the reality when the two car actually they stick together. All right, so fine, let's talk about yes.
Sir, completely inelastic collision take to बुझा
So completely inelastic collision is the collision when that after the collision, if the two body stick together, so that means they move at a common velocity. That's called actually completely inelastic collision. So if you strike something, let's say you can say that when you're going to be strike, or you can going to be that drop a ball into the mud. If the ball is get inside the mud, so that's when it stick together. That is example of the complete inelastic collision. When a policeman is going to fire a bullet inside a person body, that is also the completely inelastic collision, right? That system actually they stick together actually. Or if you drop a egg, that egg is going to be that broken into the floor, that's when it is also stick together. We can also say that that is also completely inelastic collision. And this egg is going to be that break actually because of that high acceleration when system is going to be that strike, and due to that collision actually a huge amount of force actually acting on the system. Due to that huge amount of force there will be a huge amount of acceleration. That's why something is going to be the break when they collide to each other. So the ideal situation is actually after the collision, if the two systems stick together, then that's called actually that completely inelastic collision. And in the case of completely inelastic collision, maximum amount of energy will be the loss from the system, right? All right, let's consider one dimensional elastic collision. Let's say I have this object actually m1 v on I, another object m2 which is moving at a speed v2y. This is that before the impact, and m1 v1f, m2 v2f. This is that after the case, right? So I am to find out what should be this velocity after that collision actually. Since it's elastic collision, I can say that both that momentum and the kinetic energy will be conserved. So if the momentum is conserved, I'm going to write down pi equal to that pf, which means I'll write m1 v1I plus m2 v2I equal to m1 v1f plus m2 v2f. This is actually that one equation which I get the equation from the conservation of the linear momentum. Let's say this is the equation number 1. And another equation we can write, which is kinetic energy initial must be equal to kinetic energy final. So I can write half of m1 v1 I square plus half of m2 v2 I square, right? That must be equal to half of m1 v1 f square plus half of m2 v2 f square, right? So this is the equation number 2. So I have two unknown and I have two equation actually over here to find out those v1 and v1f and the v2f. This is equation number 2. Now the problem is, if you want to solve these two equations, it's not too straightforward and it's not too easy actually. Look at this one is actually that first order equation, and second equation actually the second order, because it's a power is 2 actually. So that's why it is not easy straightforward to solve this equation. It's required at least 10 to 15 minutes if you know that every step how to going to solve this one. You will find out the solution of this two equation in your reference book in the Resnick-Halliday-Walker. So I'm not going to show that step. I'll just write down what you are going to get from these two equation. If you want to find out v1f, it should be, I'm writing, look at this, if you want you can carry this information in your head. Sometimes it is very helpful. I'm not going to say that memorize, but I'm going to show you the technique. It's a v1 plus m1 plus m2 into v2I, and it is also true exactly the same for v2f. There will be no change up to this. It's a m1 plus m2 into v1I plus m1 plus m2 into v2I, right? Is exactly the same. There is nothing difference over here. Fine. Then difference would be over here. It should be m1 minus m2. It should be 2m2. It should be 2m1, and there should be m2 minus m1. Right? So this would be actually the solution of these two equations. All right. you understand? That should be the basically the solution of these two equations. So this equation sometimes is very helpful actually. If you explain any situation, you can also find out easily. But otherwise, if you want to in writing down in terms of this kinetic energy and that moment of conservation, then it's very difficult to solve or to find out those parameter V1F and the V2F. It's very hard to find out in that sense actually. Right? So let's consider three cases according to these two equations. Let's say case number 1, when actually if I say M1 equal to that M2 and V2I is equal to the 0, right? Then which means I have two equal mass of the object. Let's say this is M1 which is moving at a speed V1I, another object is M2 which is V2I, and V2I actually is 0. Then what will happen after the impact? What should be their velocity or which direction they will move? What is this one? And this is M2. What is V2F? Right. Alright, so if I write down this equation, look at this, I'm writing again this equation for you again. So I'm going to write M1 plus M2 V1I plus M1 plus M2 V2I. It should be M1 minus M2 to M2, right? And V2F is again, it should be M1 plus M2 V1I plus M1 plus M2 V2I. It should be that 2M1, it should be M2 minus M1. This is the equation I'm supposed to write. Now look at this, since excuse me, since V2I actually is 0, so initially the second mass actually is stationary, then this will be 0, right? This one I can also say that 0. Then I will find out, since M1 equal to the M2, this part is also going to be the 0 because this will be cancelled out in that case. That means V1F would be 0 and V2F would be, since M1 equal to M2, so over here I can write this is 2M1 and this would be also the 2M1 since M1 equal to M2 into V1I, which means it should be simply V1I, which means after the impact these two objects will be simply interchange their velocities, because initially this M1 is moving with a speed V1I and this M2 is stationary, which is V2I actually the 0, and after the impact this M1 will be the 0, right? It is not moving, and this M2 will move, V2I should be V1I, right? So that's when they will be interchange their velocity. That's happen actually when you play the pool or the carom, when your cue ball is going to strike your target ball. After the impact, the cue ball should be stopped if it is exactly the equal mass, and after the impact that cue ball should be the stop and the target ball should be the move if it is exactly the equal mass and if it is a elastic collision. That should be happen in that case. Right, so now consider the case number 2. If M1 is much greater than M2 and again V2I actually that's 0, I make it simpler for you. So let's say this is a bigger mass, this is M1 which is moving at a speed V1I, and let's say this is actually that m2 which is stationary equal to the 0. After the impact, what will happen actually? So I'm not writing the second term. The second term will become 0 because if this v2i actually is 0, I'll write only the first term. It should be v1f would be simply m1 minus m2 divided by m1 plus m2 into v1i, which means uh, this ratio is going to be equal to the 1. Let's say m1 is 1000 kg and m2 actually the 1 kg. Then difference 1000 minus 1 divided by 1000 plus 1, this ratio is going to be equal to the 1. You can check that one. So it should be, that means is closely is going to be simply v1i. So that's mean after the impact, the momentum of this bigger object is not going to change at all. Now what about that v2f is going to be that 2m1 divided by m1 plus m2, right? And v1i, right? And this one is going to be the simple.
Yes, sir.
And in this case, what will happen after the impacts is this v2 will be moved, because this ratio again 1000 divided by 1000 plus 1 is going to be again the 1. Then this will be simply 2 v1i. That means after the impact, this bigger object is not going to change its momentum, whereas this smaller object will move double the speed of bigger object, right? Because we find out that is the 2 v1i. All right, so that's the case. So that's mean when you're going to be the bigger car, it's going to be the strike a smaller bike or motorcycle. So then in that case, the bigger object or bigger car is not going to change its momentum, but the motorbike should be fly off with the double speed of that one. All right. So fine. Now what about that case number 3? If we consider that opposite case, actually case number 3. In that case, I'm considering m2 each much greater than m1, and v2i is actually equal to the 0. Right? Then what I'm going to get, again the second term is going to be the 0. I'll find that v1f is going to be that m1 minus m2 divided by m1 plus m2 into v1i plus 0, right? So in that case, this is going to be that 1 minus 1000 divided by 1 plus 1000. That ratio is going to be the 1, but this time it's going to be negative 1 actually, because 1 minus 1000 is going to be something negative, right? So then I'll find out this will be minus v1i, whereas that v2f is going to be that v2f would be simply 2 m1 divided by m1 plus m2 into v1i. This system is going to be, in that case actually it should be 1 divided by 1001 is going to be close to the 0 actually. So that's why it's going to say that it should be close to the 0. That's mean what happen if I consider a smaller object which has a mass m1 and moving at a speed the v1, and if we strike with a bigger object which is m2, v2i is equal to the 0. If it is strike, after this strike this m1 will be the bounce back with the same speed but in the opposite direction, v1f, but this bigger object will be not change its momentum, it will be remain same. If it is stationary, it will be remain stationary. If it is moving, it will move at that same momentum. It will be not change at all actually. That's how actually we can explain these 3 phenomena using this equation. All right, let's talk about collision and the impulse. Collision and impulse. when a collision takes place, during that collision actually, due to the huge force actually that the system changes momentum. This change of the momentum actually we say the impulse, because this is that momentum change because a huge amount of force acting on the system very short amount of time. So that's why this change of the momentum actually we say the impulse. You can say that a best example actually when a cricket player actually hit the ball with his bat, due to that force actually that instantaneously the ball actually changes its momentum, right? Because initially it will moving towards that direction, but once it is strike at that point, that the ball changes momentum towards in opposite direction instantaneously when the bat actually going to strike that ball. So that means it's apply a huge amount of force but very short amount of time. So that's why its momentum is going to change. Like, you can also say that the baseball is also example of the impulse of the system actually. So that's mean when a huge amount of force act on a very short amount of time, due to that force actually the system changes its momentum. This change of the momentum actually say that the impulse of the system. We can say that I actually is simply the change of the momentum of a system. And this change of the momentum we can find out because we know that if you want to change of the momentum of a system, you have to apply a external force, net external force, right? And that's the force actually applied by the player on the ball. Then we can say this change of the momentum would be simply F net into the del t, which means I should be equal to that del p equal to that del p I can write is the momentum final minus the momentum initial, that must be equal to that F net into the del t, right? That is going to be actually that is called that impulse of the system, and sometimes it also called that impulse momentum theorem, this one, because if you want to find out that impulse of a system, you are going to find out the momentum, which is the change of the momentum, and that momentum will be changed because of this net force. It's not the net force, sometimes it's also called about that average force. Average force. Why is called the average force? Actually we say that in physics, let's say you have a function look like that, which is, let's say this is the position and this is that function of force over here, any function. If I find out in any particular point or position, it has a abrupt change. Abrupt change mean, I can say another way, if I get a sudden peak. So let's say in this point I get a sudden peak of that function, and instantaneously in the next second it's also dropped to the zero, right? At particular point also I make it broader, it's not a very broad, it's a very sharp peak actually we try to draw in a, it's a very sharp peak, it's like this one. This type of function actually we say the delta function. It's called that delta function in physics actually we define. And we're going to measure this delta function actually, we generally take the average of this function. And that's why it's called that average force, because when the player apply that force on the ball, it's a very short amount of time, right? Because the collision between the ball and the bat actually, that it could be some sort of millisecond. Sometimes it could be also that millisecond. It should be 1 or 2 seconds actually, right? So, and when the ball actually leave the surface of the bat, at that moment the force on the ball actually is zero, because there is no interaction between the ball and bat after that, after the hitting or after the leaving the surface of the bat. So that's why in that case I can say that next moment the force would be the zero. It's a huge peak, and instantaneously in the next moment is become to the zero, right? That's why it's look like a delta function, and in the case of delta function we are generally take the average of that function. So that's why sometimes it's also called that average force of the system. All right, so and this one, let's say consider a case, a tennis player actually serve a ball with his speed 55 meter per second, and that mass of the ball is 0.06 kg, which means the 60 gram, and that interaction time between the ball and the racket actually that 4 millisecond, right? Then I am to find out what is the average force does the player apply on the ball to serve the ball with his speed 55 meter per second. Alright, so to find out that force, I can write which is that average force. I'm supposed to write it should be change of the momentum into del T. Right, change of the momentum, I'm supposed to write mvf as final momentum minus mvi divided by del T. Now this mvi actually equal to the 0, right? It should be 0 over here. So why it is 0?
Yes, sir.
Why is initial velocity actually the 0? Because when the player serve the ball, initially he throw the ball towards the upward direction. When he's coming back, at that moment the player serve the ball towards that horizontal direction, right? So if I draw, this is my x direction and this is my y direction. So this is actually that final velocity after the collision. That is the velocity. But initially it doesn't have any x component. It has component only to the y direction. Right now I am concerned to only the horizontal direction. I am not concerned about the vertical direction. That's why this initial velocity will be the 0. Then you can write it should be 0.06 into excuse me, into 55 divided by 4 millisecond, means 4 into 10 to the minus 3, right? 10 to the minus 3, which would be simply 825 Newton. That's the average force will be active on that part. So this is the case. So that means if you want to serve a ball with 55 meter per second, if the mass of the ball is 60 gram and the collision time is 4 millisecond, then this amount of force you have to apply on the ball. At the moment is going to be that you strike the surface of the ball actually. It's a huge amount of force, right? So it's more than enough to lift off a 60 kg person actually. Some player has more than that speed. In that case, they apply more than this force. Alright, so what about if the force is variable? In that case, we will find out this impulse is simply, I need to integrate this equation, is a T1 to T2 into F into dt, because that's the impulse equation we write down. Look at this. It's a force into del T, right? So I'll just simply integrate that one to find out that impulse, which is would be also the change of the momentum of the system. You can use, if the force is variable, we can use this equation. If the force is constant, we can use that equation to find out the impulse of the system. Alright, let's talk about that collision in the 2D or 3D. This idea is same. If you understand the 2D, you can also solve the 3D. Collision in 2D and 3D. In the case of 2D, let's say I have two mass. This is M1, it's a V1I, another mass M2 V2I. So after it makes a head-on collision over here. So that means their momentum in the same direction. So after the collision, what happened? This move. This is V1F. Is a M1. It makes an angle the theta 1 over here, and this is M2. It moves towards V2F, which is actually that theta 2, right? So that's mean after the impact they move in the different direction. Now I want to also find out what should be its velocities. If I can find out the velocity, then I'll be also able to find out the kinetic energy. Then we can make a comment whether it's elastic or inelastic collision. But let's consider this is my, I can choose the different color so that I can take the component of these velocities after the impact. Let's say this is my positive x and this is my positive y, then I will find out this will be my vfx, this would be my vfy, v1 it should be the 1f and 1fy, and this should be v2fx and this should be v2fy, right? Fine. So then what I can write over here to find out this velocity, I'll simply write down that momentum conservation over here, because whether it's elastic or inelastic collision, both case we know that the momentum of the system will be conserved. So first equation is a two-dimensional case, so that's why we will take the component of this case. First I will write down the x component, it should be pix, it should be pfx. I'm taking that in terms of x component. Then it should be m1 v1i, it is towards the x direction, and m2 v2y, that is also towards the x direction. Now for final, it should be m1 v1 fx plus m2 v2 fx, right? Now
Yes, sir.
this one I can write m1 v1i plus m2 v2y. This v1 fx, actually I can write down m1 v1 f into cos theta 1. I'm taking the component of this velocity because this is my final velocity v1 f, that one I want to find out, and it's create an angle, the theta 1 over here, which should be v1 f cos theta 1 would be simply the v1 fx, right? So I'm replacing that part. Instead of this v1 fx, I'm writing v1 f cos theta 1 plus same thing over here m2 v2 f cos theta 2, right? So this is actually the x component. Now for the y component, I'll write, so piy must be equal to pfy. Then the piy is equal to the 0 because initially it doesn't have any component towards the y direction. Before the impact, both the system are moving towards that x direction, so that means momentum is only towards that x direction. It doesn't have any component towards the y direction. But after the impact, they have a component towards the y direction, right? m1 is moving towards the positive y direction, but m2 is moving towards the negative y direction. Then I'm supposed to write it should be m1 v1 fy minus m2 v2 fy. Those are the components you can find out. Now this would be 0, I can write it should be m1 v1 f sin theta 1 minus m2 v2 f sin theta 2. Now I have two unknown v1 and v2, and I have two equations. This is one equation and there is another equation for x and y component. If I solve these two equations, I will be able to find out v1 and v2, v1f and the v2f. So those would be the velocity after the impact of these two objects. Alright, if you know that velocities, then you can also tell that whether it's elastic or inelastic collision. If kinetic energy initial equal to that kinetic energy final, it should be that elastic collision, and kinetic energy initial not equal to kinetic energy final. That's going to be that in elastic collision, right? That's how we can make that whether it is elastic or inelastic collision. All right. All right, let's consider a case. I have a case where two objects is going to be strike each other. So this is the case. This is the object. This is the M1. This is moving with the speed. This is the V1, and the second object is that M2, which is moving towards that direction, is that V2. This one is given actually, that M1 actually that 0.15, M2 actually 0.3 kg, V1 actually 0.8 meter per second, V2 actually 2.2 meter per second. Now after the impact, I am to find out what should be their velocity or which direction they will move actually. Alright, to solve this one, I'll write down that equation actually. Excuse me, I'm writing this equation, which is V1F M1 plus M2 V1I plus M1 plus M2 into V2I. I'm writing in that case so that you can understand how I carry this information in my head. This is the same M1 plus M2 into V2I plus M1 plus M2 into V2I. Difference is over here. It should be M1 minus M2. This should be 2M2. This should be 2M1, and it should be M2 minus M1. So now you have this information. If you plug in those parts, you will find out this is going to be M1 actually the 0.15 kg. So 0.15 minus 0.3 is the M2 divided by sum of these. It should be 0.45 if you add, and the V1I actually into 0.8 plus 2 into M2 is the 3.3 divided by 0.45, and the V2I would be simply the minus. It should be minus 2.2, right? It's a minus 2.2. Basically it's moving to the opposite direction of your x. That's why it's with the minus over here. Now if you solve, you will find out that this V1F, I'll find out this V1F is going to be that simply minus 3.2 meter per second, and if you plug in this V2F, that's going to be that minus 0.2 meter per second. So that's when after the impact, both the block will be moved towards the negative x direction, because both are minus sign over here. And if they ask you what type of collision is it, then you can write down. So kinetic energy initial and kinetic energy final. So if you find out the kinetic energy initial, that's going to be that basically 0.744 J, and kinetic energy final, that's going to be that also 0.744 J. Since it's equal, kinetic energy initial equal to kinetic energy final, then it should be basically that elastic collision, right? It's going to be that elastic collision over here. Fine? Alright, let's say I have another case. I have a system like that. There is a block over here. It's a wooden block which has a mass is that mb, which is stationary. Velocity of this block is 0, and a bullet is coming towards this wooden block with its speed 150 meter per second, and its mass is given mb, and this is the before the impact. This surface is frictional between the block and that. After the impact, what happened, it makes a completely inelastic collision, which means the bullet would be embedded inside that block actually. So, and together they travel a distance, the d. After traveling that distance d, they stop over here. So this means they become, their final velocity becomes 0 over here. So that's why they stop. They give this information. Mass of this block actually that 2 kg. Mass of that bullet is 5 gram, and the d is given. The d is 270 centimeter, and the speed of the bullet is given as which is 150 meter per second. Now they ask you what is the frictional force between the block and that surface, because that's the frictional force actually that do the job to stop over here. Because if I draw the free body diagram, of this bullet block system, after the impact you will find out that this is the force actually. This is actually your mb plus mb into the g. This is actually your normal reaction force. This is actually that Fk, and there is some velocity actually which is that initial velocity. It's not 0 actually, that would be that velocities. So that's mean I can say over here, if I want to this frictional force since it's a, I cannot write down the total energy initial must be equal to total energy final, because there is a friction. Due to that friction there will be some loss of the energy. What I can write, I can use the work energy theorem. Net work done over here should be simply the change of kinetic energy, right? So work done, you can write work done by the normal reaction force, work done by the gravitational force, and work done by the frictional force. That should be that kinetic energy final minus kinetic energy initial. So kinetic energy final actually the 0 because it stopped over there. Work done by the gravitational force is 0. Work done by the normal reaction force is 0 because the angle between that force and the displacement actually the 90 degree, both two force, this force and this force. So work done will be simply by this frictional force, right? Then I can write this part. So work done by the frictional force will be frictional force into the displacement, and the angle between them, which is 180 degree, it should be minus half of m vi square. This is the total mass. Remember, I am writing this. M means the total mass. Then cos of 180 degree is the minus 1. It should be Fk into the d, and it should be minus half of this m. I can write the mass of the block plus that mass of the bullet, which is the total mass, into vi square. This minus sign can be cancelled out. Then I can find out this Fk would be simply this 2 is going to be that mb plus mb into vi square divided by twice d. Right, that's with the frictional force over here. Now to find out that frictional force, I need to know this displacement. I know the masses of this one, but I need to know right now this initial velocity, which is means that after the impact of that velocity, right? This is the initial velocity over here. To find out that initial velocity, I can use momentum over here. So conservation of the momentum, I can write, so initial momentum must be equal to that final momentum. So what should be the initial momentum? So this is the momentum of that block plus this is that momentum of the bullet, but after the impact they stick together, which is the mass of the bullet, mass of the block into that vi, which is the velocity, right? Now initial momentum of that block is 0 because it is stationary, right? It is not moving actually over here. Look at this, right? Come on, my system is disturbing over here. So alright, so from here actually you can find out that part actually, because you can find out this velocity, which is going to be that simply this vi this vi is going to be over here. So if you write, come on, my this way is disturbing. So it's going to be basically that simply, so vi would be simply mb vv divided by mass mb plus mb, right? So that should be the velocity. If you find out that velocity, if you plug in those values, you can find out that vi. If you can find out the vi, then you will be also able to find out the frictional force if you just plug in into over here, because you know other thing over here, right? That's how you will be able to solve this equation from here, or the frictional force they're asking to find out from this part. Alright, that's all for today. Thank you very much, guys. I'm done with you.